So, in this session we will be mostly solving problems of reaction engineering. Once again, it is a continuation of that previous session. So, a first problem, see 1. A vapor phase catalytic reaction. So, my reaction is vapor phase catalytic. The reaction is Q plus R giving S, followed Riedel mechanism. So, it is Ellie-Riedel mechanism. So, where R and S are not adsorbed. So, R is in the gas phase, S also in the gas phase. Initially, the mixture contains only the reactant in equimolar proportion, right. So, that means equimolar reactants. The surface reaction step is rate controlling. Surface reaction step is rate controlling with a constant A to B. The initial rate of the reaction minus RA in terms of total pressure is given by. So, minus, so we have to generate the initial rate of the reaction in terms of the total pressure, and the options are APT divided by 1 plus BPT, B APT by 1 plus BPT square minus R naught APT square 1 plus BPT minus R naught APT square divided by 1 plus BPT whole square, right. So, this Q is adsorbed and then we have the surface reaction. So, our overall scheme is Q plus S, reversible arrow Q dot S, right, Q dot S, and Q dot S plus R giving S. So, minus of RS. So, here we can write this is the reversible error. So, Ks C of Q dot S PR minus K of minus S PS. So, Ks if you take common, C of Q dot S PR minus PS by Ks. Now, we have to generate this Q dot S. So, Ct equal to C Q dot S plus Cv, right. Now, let us write the rate of adsorption. So, here minus of Ra is equal to Ka P of Q into Cv, P of Q into Cv minus K of minus A C of Q dot S. So, if I take this Ka common, it is PQ Cv C of Q dot S divided by capital Ka, which is the adsorption equilibrium constant. So, minus of Ra divided by Ka is 0 relative to minus of Rs by Ks. So, we have C of Q dot S is equal to Ka PQ into Cv. Now, the side balance yields Ct equal to Cv plus C of Q dot S. So, which is Cv plus Ka PQ CV. So, CV is equal to CT divided by 1 plus KA PQ. Right. So, this is not required here. So, C of Q dot S is equal to KA PQ 1 plus KA PQ into CT. So, if I replace it here, it is Ks KA PQ divided by 1 plus KA PQ CT PR minus PS divided by Ks. Right. So, the initial rate here, what we have to substitute? PQ is equal to PR, these two are the reactants, Q and R. PQ and PR is equal to total pressure by 2. Okay? And PS initially must be equal to 0 because S is the product. So, this becomes Ks KA CT into PT by 2 whole square divided by 1 plus Ka PT by 2. So, obviously, this is Ks Ka CT divided by 4, it is a constant, into PT square divided by 1 plus Ka by 2, another constant, into PT, which is A PT square divided by 1 plus B PT. Right? So, this is the answer. So, you have to note that it is a very elementary, but we have to understand the Langmuir-Hicelud approach to solve for the rate determining steps and the rate expression. So, Tomda, class. এই জায়গাটা কেটে দেবেন বলছি সে ঠিক আছে আপনি জাস্ট আমাকে ইয়েটা এনে দিন রুমালটা মানে রুমাল মানে কি ওই মশার কাপড়টা পেয়েছেন থ্যাংক ইউ ঠিক আছে থাক 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 হ্যাঁ আচ্ছা So, the previous problem what we have solved is a gate problem of around 2014 or 15. So, next this is a problem related to thermal effect to the liquid phase reaction. This is liquid phase reaction. So, basically delta V we can consider it to be 0. The reaction is A giving B. Is conducted in an adiabatic PFR. Inlet concentration of A, Ca naught, is 4 kmol per meter cube. Density of that reaction mixture is 1200 kg per meter cube and independent of temperature. This density is independent of temperature. Average heat capacity of the feed stream Cp feed is 2000 joule per kg per Kelvin. Heat of the reaction minus 120 kilojoule per mole of A reacting, mole of A reacting, if the maximum allowable temperature in this system 800 Kelvin, the feed temperature should not exceed some. So, the question is, if the maximum allowable temperature in this reaction is 800 Kelvin, then the feed temperature in Kelvin should not exceed 400, 500, 600 and 700. So, feed temperature must not exceed T naught. So, we are writing in mathematical form. So, we have to calculate the value of T naught. Right. So, you see that the data is given. So, we have to invoke this general equation of reactor. So, 0 equal to Q dot minus W dot S minus summation of theta I Cpi T minus T naught into Fa naught plus minus of delta H Rx into Fa naught into Xa. So, Q dot is 0, W dot S is 0. So, summation of theta I Cpi T minus T naught into Fa naught equal to minus of delta H Rx into Fa naught into Xa. So, Fa naught cancels out. So, what you can write that T minus T naught is equal to minus of delta H Rx into Xa divided by theta I Cpi. So, T naught is equal to T minus delta H Rx summation of theta I Cpi, right, Xa. Now, here I should not write this as T naught, okay, let me change this notation. This is T naught, this is F, so we have to calculate Tf. Just it's a simple change of notation such that it is consistent with whatever equation I am writing, okay. So, T max is 800. Now, what will be the Xa max? Xa max is 1. So, we have to calculate the condition for the maximum conversion which can produce this T equal to 800. So, T naught equal to 800 minus delta H Rx. So, let us write this delta H Rx as it is, and this Ca naught is given, rho r is given, everything is given, right. Now, Cp is in joule per kg, it is in mass basis, whereas the reaction is joule per mole, it is a molar basis. And as there is no B present in that stream, so you can write this is equal to Cpa into 1. So, point is here that you have to convert this kilojoule per mole to kilojoule per kg or joule per kg, right. And that is the issue here. So, what you can do? C or Cpf to joule per mole. So, if we think of this reaction, I have to get the molecular weight. So, because the delta H Rxn is equal to minus 120 into 10 to the power 3 joule per mole of A into I have to write this ratio mole of A divided by kg of A, right. So, it is kind of inverse of molecular weight, kilojoule per mole or kg mole, let me check. Yeah. kilojoule per mole. Yeah. So, moles of A per kg of A. Here it is kilomole per meter cube, right. What we are supplied with? We are supplied with density, right. We are supplied with Ca naught. So, Ca naught is independent of temperature. So, what you will get that and density, this density is the density of the feed and Ca naught is the temperature. So, molecular weight, or rather we can write that density which is in kg per meter cube divided by molecular weight which is in kg mole per kg, sorry, kg per kg mole, right, divided by molecular weight kg per kg mole. What I will get? This will be something in kg mole per meter cube, which is Ca naught. Right. So, kg mole per meter cube, this is given as 4, and rho it is given as 1200. So, obviously m, which is in kg per kg mole, this is 1200 divided by 4, which is 300. So, mole, this is in kg per kg mole into 1 kg mole 10 to the power 3 mole equal to 300. So, m, kg mole cancels out. So, m in kg per mole is 300 into 10 to the power 3. Right. So, here it is mole per kg. So, we have this as minus 120 into 10 to the power 3 joule per mole of A into 1 divided by 300 into 10 to the power 3, this mole per kg, right. So, this will be expressed in minus 12 divided by 30. So, it is 2 divided by 35. So, it is minus 0.4 joule per mole, per kg of A. So, that is to be substituted there, and Cp is 200. So, from there we can calculate what will be the maximum value of this. Cpa is joule per kg per Kelvin. So, from there actually we can calculate the value of this T naught. So, what will be the value? I think I have done some mistake here. 0.5 into, no, it is not going to give me this value. So, where is the mistake? Let me point out. 120 kilojoule per 120 kilojoule per A. Density of the reaction mixture kg per meter cube. Ca naught is 4 kg. Sorry, it is 4 kg per this one. So, here I have written 4. So, it is kg mole per meter cube, 1200 m is 300 kg per kg mole, 300 gram per gram mole, and here I do not know whether it is joule kilojoule per mole It may be kilojoule per kg mole basically. So I think it will be kilojoule per kg mole, I think. So whatever it is, the strategy will be like this, and you see the density and concentration, they are given specifically to find out the molecular weight. So that's the crux idea. There may be some calculation error or maybe the misinterpretation of data which I have copied here. So anyway, that's not the issue, but here this is the idea how to deal with the problem. So the next problem is that here. Two problems and reaction. Okay, let me check it out. No. Okay, see this problem. Let's consider a zero order reaction. This is problem 3. Zero order reaction followed by a first order reaction. What is the scheme? A series reaction, A giving R and R giving S. This is K1, it's a zero order, it's K2, first order. The series reaction is being conducted in a plug flow system, PFR. Determine the optimum space time required to achieve maximum CR. Tau optimum for CR equal to CR max. Right. So here you see the first order reaction, let's consider a zero order followed by first order. Reaction is being conducted in a plug flow system, determine the optimum space time. So we have to assume constant volume system as no information is given, where batch and plug flow design equations are identical. So we can deal with this plug flow as well. So minus of dCA dt is equal to K1, right, because it is zero order. So Ca equal to Ca naught minus K1t, and that will be the equation for t less than Ca naught by K1, right. Next, dCr dt equal to K1 minus K2, K1 minus K2 Cr. Okay, dCr dt is equal to K1 minus K2 Cr. So what will happen? This dCr dt plus K2 Cr equal to K1, my integrating factor is e to the power K2t. So e to the power K2t into Cr, t equal to 0 to t is equal to K1 into e to the power K2t dt, integral from 0 to t, K1 e to the power K2t divided by K2, 0 to t. So K1 by K2 e to the power K2t minus 1. So Cr is equal to K1 by K2 1 minus e to the power minus k2t. So, this is the expression of CR, where CA is simply decreasing down, right? Yeah. And this is true for let me check K1t. So, what will be the nature of the graph that we have to understand? CA naught goes to 0 like this, and this is the CA naught curve, CA curve. This is CA and this is CA naught. So, when it becomes 0, I have this, okay, and this is true for t less than CA naught by K1, that we have to understand, and this is the crux. So, for t greater than CA naught by K1, dCr dt is equal to minus K2 CR, right. So, CR is equal to some CR naught into e to the power minus K2t. So, CR will be like this. So, obviously, CR will be maximum at this CA naught by K1, right, at this CA naught by K1. So, that will be the maximum value of CR. So, what will happen? So, K1 by K2 into e to the power K2 into t, t we can place as CA naught by K1. It is not, yeah. So, the optimum time, yeah, the time we have solved, actually we have to ask for the time, right. So, tau optimum is this one, which is CA naught by K1. So, that will be our answer, right. So, that is the answer to this problem, and we have to understand not from the pure this derivative equal to 0 point of view, because it has got a discontinuity of the derivative of the CA curve here. So, actually we have to understand that there are two different regimes of this change for R and concentration change for R. So, that is the issue here. So, next let us go to the next problem. Okay. So, a problem that RTD curve of a system is given by this. This is 3, this is 7, and let us say this is 12, let us say, right. And this value is Emax. So, first question, what is Emax? And second question, what is the mean residence time? And T is in minute maybe. Right. So, you see, we know that area under this E curve, ET dt, it's equal to 1, and it's a triangle, its base is 12 minus 3, it's equal to 9, right. Okay, remember, yeah, 12 minus 3 equal to 9. So, it is half into 9 into Emax equal to 1. So, Emax is 2 by 9, right. Half area of the triangle, half base is 9 into Emax, the vertical height, equal to 1. So, Emax we can calculate as 2 by 9. Next, what is the mean residence time? So, this Emax is 2 by 9, right. So, we can understand that here the span is around it's 4 and here it is 5, right, and it is a kind of asymmetric triangle. So, here this Tm should be slightly higher than 7, it will be around 8, okay. But if you have got an options that it is 15 or 10, okay, 2.5, maybe 11 and 8. So, you can directly conclude that answer is 8. But if the options are not given, what you will do? You see, then it is tedious, it is really tedious. We know that Tm is integral 0 to infinity T into Et dt, and for this specific case it is 3 to 7 T into Et or E1 T dt. Let us call this curve as E1 or function E1, and next it is 7 to 12 E2t into T into dt. Now, what are the equations of this E1 and E2? Right. So, you can write that E1, see, 2 points are given, 2 point coordinates we know. So, E1 minus 0 here divided by, we are using simply y1, y minus y1 divided by x minus x1 is equal to y2 minus y1 divided by x2 minus x1. This equation of straight line where 2 points are given, right. So, E1 here, E1 and let us say T. So, E1 minus 0 divided by T minus 3 is equal to 2 by 9 minus 0 and divided by 7 minus 3. So, it is 2 by 9 divided by 4. So, it is 1 divided by 18, right. So, E is equal to 1 by 18 or E1 is equal to 1 by 18 into T minus 3. Now, for E2, let us consider a point here. This is E2T, right. So, E2 minus Emax, which is 2 by 9, T minus 7 is equal to 0 minus 2 by 9 divided by 12 minus 7. So, 2 by 9 divided by 5, so 2 by 45 and E2 is equal to 2 by 9 plus 2 by 45 into T minus 7. So that two equations E1 and E2 we have to substitute, we have to do this tedious integral, and then we can solve for actually the Tm value. So that's the idea of this overall equation, right? So the similar problem, you see, this may be 5, I think, whatever. A batch radioactive material is dumped in Columbia River at Hanford, Washington, right. At Bonneville Dam, about 400 kilometers downstream, the flowing water, the rate of the flowing water. So basically what is happening? Here you are dumping the radioactive tracer or radioactive material. And the flow rate, 400 kilometers downstream there is a dam, right, this distance is 400 kilometers, and the flow rate Q is equal to 6000 meter cube per second. At the downstream 400 kilometers, the flowing water is monitored for a particular radioisotope. This radioisotope we are trying to detect, which has got T half greater than 10 years, right. So over this time interval, so there will be negligible change of concentration. So it's non-reactive, right. The data shown in the figure. So what is the concentration? It's a very similar plot. This and this. This is 20 days, this is 35 days, this is 125 days, right, and the concentration is 10 to the power minus 6, and the unit, this scale is unit of radioactivity, whatever it is, per meter cube. So this is equivalent to concentration, right. So what is the question? The question is how many units of radioisotopes were introduced in the river. So this M that is asked. How many units of radioisotopes were introduced? So you see this is the concentration. Concentration per unit, this unit per meter cube, okay. So we can say that M is equal to integral 0 to infinity Q naught or Q into Ct dt, right, simply it is the integration, because Q is in meter cube per second, Q it is meter cube per second, Ct it is in unit per meter cube, and T if it is in second, then second cancels out, so we will get the meter cube. So here it will be in days. So actually this Q is constant, so it is 6000 meter cube per second, and this is 24 into 30 into 30 meter cube, this is being multiplied meter cube per second. So it is this into 24 into 30 into 30 meter cube per day multiplied by Ct dt, right. So it is half into 125 minus 20, 105 into C naught, which is 10 to the power minus 6 This is in unit per meter cube into day. So, day cancels out, meter cube cancels out, I will get the unit. Okay? So, that is half divided by 10 to the power 6. So, 3000, so it is 10. Right. So, from there we can calculate what is the unit which we have, unit of this radioactive, this material what we have dumped in the upstream. This problem I think we have solved previously. Okay, it's over. Okay. So, this problem states that at present our 6 meter cube tank reactor, volume 6 meter cube tank reactor gives 75% conversion for a first order reaction A giving R. However, since the reactor is stirred with an underpowered paddle turbine, we suspect incomplete mixing and poor flow pattern in the vessel. A pulse tracer shows that this is so and gives the flow model sketched in the figure 5. What is the flow model? Actually, this is 2 meter cube effective volume. This is V naught XA equal to 0.75 and there is a dead volume Vd equal to 4 meter cube. Right. What conversion we can expect if we replace the stirrer with a powerful enough to ensure mixed flow? So, XA prime if V effective is now 6 meter cube. So, we know that V by Fa naught equal to XA divided by, here it is a first order liquid phase reaction, 1 minus XA. So, V is 2 meter cube here. So, 2 divided by Fa naught, Ca naught is not given. So, K into Ca naught is equal to XA 0.75 divided by 1 minus 0.75, 0.25, that is 3. So, K Ca naught divided by Fa naught equal to 3 by 2, which is 1.5. In the next case, V by Fa naught, which is 6 divided by Fa naught, it's equal to XA divided by K into Ca naught into 1 minus XA. So, we have to find out XA. So, 6 into K into Ca naught divided by Fa naught. So, 6 into 1.5, 3 by 2, because K Ca naught by Fa naught we have already found. So, this is equal to 9, that is xa by 1 minus xa. So, 9 minus 9 xa equal to xa. So, 9 by 10, which is 0.9, will be the xa. So, that is the answer. So, that is typically the idea that if we change that volume of the CSTR, what will be the effective volume of the CSTR, what will be the change in conversion. So, here a catalytic slab, this problem what it states, a catalytic slab thickness, catalytic slab thickness is L. Width and length are much greater than L. So, actually we can think of this sort of shape, right. So, here this is L. Is used to conduct a first order reaction, A giving R or A giving B. So, at 450 Kelvin, the Thiele modulus of the system MT equal to 0.5, right. The activation energy of that first order reaction is 100 kilojoule per mole. The effective diffusivity of the reactant in the slab can be assumed to be independent of temperature. So, dE is independent of temperature, right. An external mass transfer resistance can be neglected. If the temperature is increased to 470 degree Kelvin, 470 Kelvin, the question is effectiveness factor is what? What will be the effectiveness factor? So, you see Thiele modulus is 0.5, right. Thiele modulus is 0.5, n equal to 1, and you see that Thiele modulus of the system is 0.5, the activation energy of the first order, the effective diffusivity is constant. So, Thiele modulus is L under root of K by dE, right. So, we can calculate actually the change in the Thiele modulus, because L, this is K naught into e to the power minus E activation by RT divided by dE. So, MT2 by MT1 is MT2 by MT1 is e to the power minus EA by RT2 by e to the power minus EA by RT1. So, you can find out this MT2, right. So, yeah, actually see there is a trick in this question, because even if you find this Thiele modulus, how will you calculate the effectiveness factor? because MT is 0.5, right. So, when MT is less than or around 0.5, we can say that Thiele effectiveness factor is 1. So, even if I change the Thiele modulus, there is no change, and if we are increasing the temperature, so MT will be slightly changing. So, we have to check that. Okay, no, I think no. This we have to use that epsilon equal to tan hyperbolic. We cannot say that this is 0.4. It is true for 0.4, but we have to use this equation tan hyperbolic MT by MT. So, epsilon 2 by epsilon 1 is tan hyperbolic MT2 by tan hyperbolic MT1 into MT1 by MT2. So, MT2 MT1 ratio we have calculated and MT2 we have calculated. So, therefrom we can find out the effectiveness factor, because for the slab this is the relation. Okay. So, that is a good problem to deal with, and that is why we are provided with this slab, because for the slab the relation between the effectiveness factor and Thiele modulus is pretty simple. Okay, here is another RTD problem. It's a gate problem basically. A pulse of concentrated KCl solution is introduced as test. So, pulse test concentrated KCl as tracer, right, into a fluid entering a reaction vessel having a volume equal to 1 meter cube. So, this volume is 1 meter cube, V reactor, and the flow rate is equal to 1 meter cube per minute. The concentration of the tracer measured in the fluid leaving the vessel is shown in the figure. So, what is that? So, this is C 20 by E, this is 50 second, this is 20 second. The flow model parameters that fit the measured RTD in terms of one of the following mixing element, namely the volume of PFR, mixed flow volume Vm and dead space volume Vd. So, what are the options? Options are given like this. Here this flow model is consistent with plug flow volume equal to 1 by 6 meter cube, mixed flow volume equal to half meter cube, and dead volume equal to 1/3 meter cube, and so on and so forth. So, this type of options were given. So, we do not have to look into the options, we can directly calculate. See, here tau total is equal to V by V naught equal to 1 minute, and that is equal to 60 seconds. So, out of which 20 seconds, so tau PFR, the tau P is 20 seconds. So, obviously Vp is 20 divided by 60 is 1/3 meter cube, right. Vp equal to 1/3 meter cube. Next, 2/3 meter cube is dedicated to CSTR and dead space. So, here you see from this point the concentration, how the concentration of the CSTR changes, e to the power minus t divided by tau m, and if it is attached with the PFR in series, then C naught into e to the power t minus tau p by tau m. Right. So, if we consider the origin from here without going into complexity, and we can use this relation. So, 20 is equal to C naught into by E at t equal to tau m. Right. So, sorry, this C equal to C naught by E. So, C naught is 20, so it will be 20 by E, and this space is tau m. So, tau m is equal to 30 second, because 50 minus 20 is 30. So, tau m is equal to 30 second, and essentially tau m is 30 second, and Vm is 30 by 60 is equal to half meter cube. So, obviously the total volume is 1 meter cube, the PFR volume is 1/3 meter cube, MFR volume is half meter cube. So, dead volume is 1 minus half plus 1/3 equal to 1 by 6 meter cube. So, my answer is Vp is equal to 1/3 meter cube, Vm is equal to half meter cube, and Vd is equal to 1 by 6 meter cube. Right? So, that is the answer. So, just another gate problem. This is a problem attached with a graph, and again it is an RTD problem. What is that? A CSTR has a long inlet pipe. See, CSTR with a long inlet pipe, which means a PFR and a CSTR in series. A tracer is injected at the entrance of the pipe. The E curve obtained at the exit of the CSTR is shown below. Right. The E curve shows this sort of profile. So, curve is given with numerical values. This is 5. Right. This is 5. And here in this concentration unit, we have a 0.05 here. So, assuming plug flow in the inlet pipe, the ratio of the volume of the pipe to that of the CSTR. So, here it is 0.05. So, obviously, we can say that C at tau m is equal to C naught by E, which is 0.05 by E. Right. So, 2.23. So, whenever it is 0.023 something like that, so you mark this 0.023 or something whatever, which we can write that 0.05 by E. So, you mark this as tau m. So, this is basically tau m, not from the inlet. Right. So, this is 5, and this you calculate and find out the ratio. So, that is all about reaction engineering. We have solved multiple problems. A lot of the problems are from GATE, right? If time permits, I will go for another reaction engineering problem solving class. So, in the next session, we will start mechanical operation. Thank you.